students. In this video, I am going to explain real gases, that is deviation from ideal behavior, states of matter topic. In previous session, I had discussed about Boyle's law, Charlet's law, Avogadro's law, Gay-Lussac's law, ideal gas equation derivation and R values. Our universal gas constant when we are taking joules, when we are taking atmosphere, calories, everything I had explained. But in this video, I am going to teach for you ideal gas, real gases. Before going to the real gases, first we look into the ideal gas. Ideal gas already had discussed, but briefly I am explaining here. Ideal gas is nothing but the gas which obeys all gas laws. The gas which obeys all gas laws at all pressures and temperatures. I have written here, at all pressure and temperatures, all gas laws obeys. That gas we call it as ideal gas. But ideal gas is completely hypothetical. So no gas behave like a ideal gas. Maximum what we are learning, all gases are real gases only. So why? So what is the reason? See students, according to kinetic molecular theory of gases, ideal gas is nothing but what are two properties they had given? See, volume occupied by gas molecules is negligible when compared to the total volume of the container. See, I am going to draw one simple diagram to understand more better. See this one. I have taken gaseous molecules. Like this. Okay, this is in a container. I have taken gaseous molecules. You can apply pressure, or else in any method you can bring all gas molecules one side. These are all gas molecules one side, just like this. Here it is occupying all gas molecules, it is occupying here, right? In this space it is sufficient, this space is sufficient. Now these are all gas molecules. If you increase the pressure, what happened? Volume decreases. If you decrease the pressure, volume increases. That we have learned, right? So with the help of pressure, all gas molecules is bringing one side. So now only this much space it is occupied as of now. That is the first point. See, volume occupied by gas molecules is negligible when compared to the total volume of the container. This is the total volume of the container. When compared to total volume of the container, this one we can neglect. This one, this small, we can neglect. That is the one of the what is this property for according to kinetic molecular theory of gases, which obeys the ideal gas equation. Okay, now second one, attractions between gas molecules are negligible. So who and all satisfy these 2 points, those are all behaves ideal gases. But no gas is ideal gas. All gases behave like a real gases. See, look into the students. See, again you can take the volume. Again you can take the container. I am taking some gaseous molecules here. Okay, gaseous molecules are sitting in the vessel, means definitely either they have attractions or repulsions. So either attractions or repulsions will be there. But what kinetic molecular theory of gases is telling, attractions between gas molecules are negligible. Yes, these two we call it as faulty assumptions. These two are faulty assumptions. So kinetic molecular theory had given, so when it is applicable, ideal gas time it is applicable, but no gas is ideal gas, right? So see, I am showing another points. What is a non-ideal gas? Non-ideal gas also call it as real gases. Okay, and ideal gas we call it as perfect gas. Some textbooks they had given perfect gas also. Non-ideal gas are also call it as real gases. Real gases is nothing but the gas which do not obey gas laws at all temperatures and pressures. What I gave starting definition, ideal gas is nothing but the gas which obeys all gas laws at all pressure and temperatures. But the gas which do not obeys, make a note, do not obeys gas laws at all temperatures and pressure, that gas we call it as non-ideal gas. Non-ideal gas also call it as real gases. Okay, see, I have written one more point here. The gas which obeys gas laws only at low pressure, high temperatures, called real gases. So ideal gas is nothing but at all temperatures and pressures, but The gas which obeys only ideal behavior at low pressure and high pressure, though low pressure and high temperature, those gases we call it as real gases. Okay students. So why all gases are behaving like real gases? Because above what we have taken, two assumptions are faulty assumptions. Faulty assumptions. So first assumption, what is that? Volume occupied by gas molecules is negligible when compared to the total volume of the container. Next one, what we have taken, attractions between gas molecules are negligible. But those two are faulty assumptions. Faulty assumptions. So what real gases is showing? Tell me, real gases. So telling real gas, if it behaves as a real gas, then definitely the volume, what is this? That is not negligible. That is not negligible. What is not negligible? Volume occupied by gas molecules is not negligible. See, you have taken container like this, the gas molecules. Why it is not negligible? Maybe you are taking more gas molecules, or else you are taking, what is this, bigger particles, each one bigger volume, bigger gaseous particles. Then it is not possible. Then it is not negligible. Then it is not negligible. That is the first one. What is the second point, students? Attraction between gas molecules are negligible, I said. So kinetic molecular theory said. But students, if you have taken gaseous molecules in the vessel, definitely they have attraction forces or repulsion forces. Suppose you and your friend sitting together. If best friend means attractions. If you are that he is just a classmate or she is classmate or else enemy, there is no attractions, repulsions. Definitely, what is between student feeling, same here between gas molecules also. If attractions is there, or else repulsions will be there. Repulsions will be there. Okay, so but kinetic molecular theory said there is no attractions, repulsions. That's why gas behaves as ideal gas. Okay, ideal, you don't have attractions between your friend and you, and no repulsions between you and your friend. Whatever you are listening class is perfect, right? But always it is possible? No, definitely you people can talk sometimes, right? So that's why if you are sitting with together, then either definitely attraction forces are there or repulsion forces are there. That is the best understanding example. Okay students, now suppose, see students, real gases. Okay, once to understand more better, first I will give you ideal gas equation. What is ideal gas equation? Ideal gas equation, PV equal to nRT. If any gas behaves as ideal gas, then definitely it satisfies this formula, PV equal to nRT. But what I said, all gases are real gases, right? For real gases, tell me, PV not equal to RT. But when PV equal to RT, nRT, when PV equal to, if you multiply with some term, Z nRT, that Z only we call it as compressibility factor. That Z only we call it as compressibility factor. That I will explain. Before going to that, I will give the graphical explanation. See students, graphical explanation. So we have taken Boyle's law, right? So pressure versus volume we have taken. If you increase, this is the pressure. The y-axis I have taken pressure. If you move bottom to top, pressure increases. As we move across this left to right, then what happened? Volume increases. So if you decrease the pressure, what happens, students? Volume increases. This is what? Boyle's law, right? So this is ideal gas. This is what, students? Ideal gas. Ideal gas. But all gases are behaves as real gases, right? See real gas how it is now, like this. See deviation. Some deviation is there. See, to understand more better, see I am taking, what is this students? At low pressure, high temperatures, all gases behaves as ideal gas. But see, what is this? Here, this is ideal gas, right? This is real gas. This one is real gas. Second one is real gas. Now what is the volume? Here if you line here, volume, if you draw the line here, volume, see here, see here, this is volume. As we move left to right, what happened? Volume increases. As we move left to right, volume increases. This is what volume? This is ideal gas volume. This is a real gas volume. Which is greater volume? Real gas volume at high pressures. At high pressures, at high pressures, what happens, students? Volume of real gas greater than volume of ideal gas. Right? This, it shows positive deviation. It shows positive deviation. At high pressure we have observed this one. Okay, and why it is V real gas is greater? What happened, students? Here maybe, suppose if you have taken a container like this and I am taking gaseous molecules like this. Okay, now these two gaseous molecules I am writing here. Gaseous molecule 1, gaseous molecule I have taken like this. Okay, this is normal distance. Suppose between these two repulsive forces are there. This is the molecule and this is the gas molecule. Between these two repulsive forces are there. Then what happened? One gaseous molecule here and one gaseous molecule here. What happened? So distance increases. Distance increases. That means volume increases. Volume increases, right? So that is the finally what you will say, volume of real gas is greater than volume of ideal gas is nothing but maybe there what type of forces are there. So here what is the dominating one? Intermolecular repulsions. Intermolecular repulsions dominates. Okay, now next one, case 2. This is case 2 I am explaining. Here this is intermediate pressure, students. This is intermediate pressure. This intermediate pressure, ideal gas, what is this? Ideal gas behaves as a real gas behaves as a ideal gas. Here PV equal to nRT. Here volume of real gas equal to volume of ideal gas. Volume of ideal gas. Now negative deviation. This is negative deviation. Here also again you can take graph like this. Okay. Here what is the, students? Here what is this? This is real gas. This is ideal gas. Right? Right or not? Now volume of ideal gas is greater. Now volume of ideal gas is greater. Then you can write volume of ideal gas, volume of ideal gas greater than volume of real gas. Then what happened? Why it is like that? Again you can consider the container. Here gaseous molecules are there. Now what happens, students? I am taking two molecules. I am writing here two molecules. Actually like this condition. If there is attraction forces increases, then what happened? These two very close each other. Very close each other means distance is less. Distance is less is nothing but definitely volume of the real gas decreases. Volume of the real gas decreases. That you can write here. What is the, students? Attractions here, intermolecular attractions. Your intermolecular attractions dominates. Clear? And this is what we call it as negative deviation. From graph you will get questions. That's the reason I am writing all the points where it is here. This is negative deviation. Graph we have observed three main points, students. See, once again I am showing here. See, what is this? This is here V real gas, volume of real gas is greater than volume of ideal gas when repulsions dominates. But when equal, both when this is intermediate pressure, when real gas, volume of real gas equal to volume of ideal gas. Next one, at very low pressures, what happened? Volume of ideal gas greater than volume of real gas. Real gas volume, why it is decreases? Maybe attraction forces are dominating. Clear, students? Okay. Now to explain this one. So to explain deviations we are using compressibility factor. Just now I said if ideal gas means PV equal to nRT, but real gas it will not obeys PV equal to nRT, no. But when PV equal to nRT, if you multiply with the term Z, it is equal to the PV equal to nRT. What is Z here? Z equal to PV by nRT. What is this Z term? We call it as compressibility factor. When gas we can compress, when it is converting into liquid, when it is showing the more deviation graph. So I will show compressibility factor, which is represented by the letter Z. Okay, students. Now see, compressibility factor Z equal to volume of real gas by volume of ideal gas. Here also three cases like I can explain, then you can understand very easy way. Now see, when suppose Z equal to 1, what happens, students? If you substitute here Z equal to 1, PV equal to Z into nRT. So PV equal to 1 into nRT. Then PV equal to nRT. When PV equal to nRT, ideal gas behavior. Right. So then see, suppose if you substitute here volume of real gas by volume of ideal gas equal to 1. So then volume of real gas equal to volume of ideal gas. That is nothing but Z equal to 1. At Z equal to 1, volume of real gas equal to volume of ideal gas. Suppose imagine at STP, what is this? At STP, same volume, both real gas and ideal gas have same volume. Suppose ideal gas, if you have taken 22.4 liter volume, okay, V ideal is 22.4, even V real also 22.4 liter volume, same volume. Okay, now next condition 2, Z greater than 1, I will show. So what is this, students? Next, for real gases, Z greater than 1. Z equal to what I said here, volume of real by volume of ideal. Here, volume of real gas greater than volume of ideal gas. When it is possible? If numerator value is more, means Z greater than 1. It is possible. Okay, students, see, that means what is this temperature? Volume of the at STP, suppose volume of ideal gas equal to how much? It is 22.4 liter. Now at STP what happened? Volume of real gas is greater than 22.4 liter. Volume. You can see like hydrogen gas and helium gas. I can show the graphs also. Hydrogen gas, helium gas, Z greater than 1. Compressibility factor is very high. Converting into liquids is very difficult. Very difficult. Okay. So there 22. It shows volume greater than 22.4. Next case 3. What is the case 3 here? V Z equal to V real by V ideal. See here, students, Z less than 1. If Z less than 1 is nothing but what happens, students? Volume of real gas less than 22.4 liter volume. So that is 3 cases. Now I will show compressibility factor graph. See, students, we have taken already this graph Z versus P. So like Boyle's law we have taken now. What is the Boyle's law? P is inversely proportional to volume. PV equal to K graph, right? In previous videos, if you take PV versus P at PV versus V, he'll get straight line. That is ideal gas behavior. See, here we are getting straight line. This is the graph. Here This is ideal gas behavior. Even real gas also behaves like a ideal gas when it is possible low pressure, high temperature. Low pressure, high temperature. So here Z equal to 1. And some are showing like this, Z greater than 1. Hydrogen gas, helium gas. Because they are small size atom. Due to small size atoms. Due to small size. So it is Z greater than 1. So very small sized atoms, more repulsions, more repulsions is nothing but here what happens students, Z is greater than 1, more repulsions, more repulsions. Now next one, some are like this, Z less than 1, Z less than 1. Generally what and all gases we are taking, NCH3, CH4 gas, and NH3 gas, like this we are taking. Okay, see, this is at this, but starting it is Z equal to 1 only. That means starting it behaves like a ideal gas only. But if you decrease the pressure, if you are increase low pressure, if you this is pressure means left to right it is increasing. Starting it is behaves like a ideal gas only. Even hydrogen and helium also. If you increase the pressure, then what happened? Molecular repulsion forces increasing. That's why Z greater than 1 it is showing. But here low pressure it is Z less than 1. Z less than 1. This is Z less than 1 graph. This is Z greater than 1 graph. Z greater than 1 graph. Okay, correct. Z greater than 1, Z less than 1. Here compressibility, here compressing gas is very easy at low pressures, converting into liquid. But here see, if you are showing graph, increasing pressure means at high pressures all gases behave like a Z greater than 1 only. Compressibility is difficult. This is compressibility factor, students. So finally everybody understood. So CH4 gas, CO gas, different, even CO also, and H3 and CO gases, they will last here. When Z greater than 1, Z less than 1, why hydrogen and helium Z greater than 1 it can show more repulsive forces. Here in intermolecular forces are intermolecular forces, that is attraction forces. Intermolecular attraction forces are more at low pressure. Increase the pressure, there also intermolecular repulsions increases. If repulsions increases, compressibility is greater than 1. Then compressibility is greater than 1, liquefaction of the gas is very difficult. Okay, so with this I had completed compressibility factor. And next one, what is that, students? And starting ideal gas behavior and non-ideal gas behavior, all the points. So and next one more, and what is this? Van der Waals equation. I am going to explain Van der Waals equation in the next video, and I hope everybody understood this topic. Please give likes and share to other students. Thank you. Thanks for watching.